Hi guys, welcome back to my channel. So in this tutorial we are going to look at this integral, this definite integral from 0 to pi over 2 of tan of x divided by 4 times the natural logarithm of tan of x squared plus pi squared dx. So we are going to use the King's property in order to solve this integral. So if you haven't subscribed to my channel yet, make sure you hit the subscribe button for more engaging content like this. So let's solve this integral. So first we are going to use the King's property, and the King's property has been stated already, which is here. If you have the integral from a to b of f of x dx, that can be written as the integral from a to b of f of a plus b minus x dx. So in this case, our a is equals to 0 and b is equals to pi over 2. So let's use the King's property on our integral. So the integral from 0 to pi over 2 of tan of x all over 4 natural logarithm of tan of x all this squared plus pi squared dx. Using the King's property, this is written as the integral from 0 to pi over 2, the same limits of tan of pi over 2 minus x, because a plus b is pi over 2, that is 0 plus pi over 2, divided by 4 natural logarithm of tan of pi over 2 minus x squared plus pi squared dx. So let's look at pi over 2 minus x. Tan of that, tan is sine over cosine. So we have sine pi over 2 minus x. Sine pi over 2 minus x is cosine of x. That is using the double angle identity. Cosine of pi over 2 minus x is equals to sine of x using the double angle identity. So in this case, our tan of pi over 2 minus x is equals to sine of pi over 2 minus x divided by cosine of pi over 2 minus x. And this is the same as cosine of x over sine of x. And that is just equal to the cotangent of x. Or you can say 1 over tan of x, just like that. So this one is cosine of x and this is sine of x, that is using the double angle identity. And you just plug them in, then you get 1 over tan x as tan pi over 2 minus x. So wherever we see tan pi over 2 minus x, we can plug in 1 over tan x. So our integral now becomes the integral from 0 to pi over 2 of tan 1 over tan of x. So the denominator can be written the numerator, 1 over tan of x divided by 4 natural logarithm of 1 over tan of x, like that, all this squared plus pi squared dx. So in the end, this one simplifies to the integral from 0 to pi over 2 of 1 over tan of x, I'll leave this for now, divided by 4 natural logarithm of 1 over tan of x, that is equal to negative logarithm of tan of x. So that is negative logarithm of tan of x, that is using the laws of logarithm, plus pi squared dx. And this is the same as integral from 0 to pi over 2 of 1 all over tan of x over 4 negative natural logarithm of tan of x squared, that is positive natural logarithm of tan of x, all this in a square plus pi squared dx. So this is the same as I all along. This is I, this is I. So this is I. Our original integral, we can also call that I, because they are the same. That is just by using the transformation from the King's property. So we can do I plus I now. Our original I is the integral from 0 to pi over 2 of tan of x divided by 4 natural logarithm of tan of x, all this in a squared plus pi squared dx. Our I transformed by the King's property is the integral from 0 to pi over 2 of 1 all over tan of x divided by 4 natural logarithm of tan of x, all the squared plus pi squared dx. I plus I is 2i. This one we can combine this one as integral from 0 to pi over 2 of tan of x plus 1 over tan of x. In the numerator, the denominators are the same, so there's no, just have to write it again, of tan of x squared plus pi squared dx, like this. So we can simplify the numerator. 2i is going to be the integral from 0 to pi over 2 of this. The numerator can be simplified as tan squared x plus 1 all divided by tan squared all divided by tan x, and the denominator will stay the same, natural logarithm of tan x all squared plus pi squared dx. 2i is going to be the integral from 0 to pi over 2 of tan square x plus 1 all over tan x times 4 natural logarithm of tan x squared plus pi squared, all this dx. So now we are going to use a u sub here. So at this point, let's do a u sub. So we can let u to be equal to the natural logarithm of tan of x. So let's do the derivative. Du dx is going to be 1 over tan of x. Then we differentiate tan, that is going to be secant square x dx. No, it's not dx here. So in that case, our du is going to be 1 over tan of x times secant square x dx. What about the change in limits? When x is equal to 0, we have u to be equal to the natural logarithm of tan of 0. Tan of 0 is 0, then natural logarithm of 0 is negative infinity. When x is equals to pi over 2, u is going to be the natural logarithm of tan of pi over 2. Tan of pi over 2 is infinity, natural logarithm of infinity is positive infinity. So our limits will change from negative infinity to positive infinity. So we have our integral now. So the integral 2i is going to be, the numerator can also be written as secant square x. That is using the property from the Pythagorean theorem, from 0 to 2 pi over 2. This can be written as 4 natural logarithm of tan of x all squared plus pi squared times the numerator can be written as secant square x. So we have secant square x divided by tan of x dx. That is by bringing this one over there and then changing this one to secant square x. And this one is du, which is our du over here. So we can now take everything from the x world into the u world. So in the u world is integral from negative infinity to positive infinity of 1 all over 4 natural logarithm of tan is u. So we just replace that with u. So that will be u squared plus pi squared times the whole of this is du. That is from here. And now our integral now reduces to the integral from negative infinity to positive infinity of 1 all over 4 u squared plus pi squared du. So 2I is going to be, you can divide the numerator and the denominator by 4, which is the integral from negative infinity to positive infinity of 1 over 4 divided by u squared plus pi squared over 4 du. 1/4 is a constant, it can come in front. Integral from negative infinity to positive infinity of 1 all over u squared plus this one can be written as pi over 2 all squared du. So we know that the integral of 1 all over x squared plus a squared dx is 1 all over a times the tan inverse or the arctan of x over a. So this looks like this. Our x here is equals to u and our a is equals to pi over 2. So we can just use that identity to solve our integral. So 2I is equals to 1/4. And then if we want to integrate, that would be 1 over a. Our a is pi over 2 times the arctan or the tan inverse of x over a. Our x here is u over a, pi over 2. And we are integrating that from negative infinity to positive infinity. So 2I is equals to, this will cancel, and that would be 1 over 2 pi. And then we can take the limits. So we have limit as k approaches infinity of tan inverse of k over pi over 2 minus limit as k approaches negative infinity of tan inverse of k over pi over 2. That is just plugging in our limit. So 2I is going to be 1 all over 2 pi. As k is approaching infinity, then tan inverse of k over pi over 2 is going to be approaching infinity as well. So this will be infinity, so tan inverse of infinity, that is going to be approaching pi over 2 minus, as k is approaching negative infinity, then tan inverse of k over pi over 2 will be approaching negative pi over 2. So minus pi over 2, like that. So in the end, 2I is going to be 1 over 2 pi. This is just pi over 2 plus pi over 2, which is 1 over 2 pi times pi. Pi over 2 plus pi over 2 is pi. So in the end, you have 1 over 2. So 2I is going to be 1/2. So in that case, our I is going to be 1 over 4. So therefore, our integral, which is I, the integral we are asked to evaluate, which is our original integral, is just equal to 1 over 4. So that's how we solve it. So you can just write it down there and wrap up the video. So which is the integral from 0 to infinity, pi over 2 of tan of x all over 4 natural logarithm of tan of x all this squared plus pi squared dx. This evaluates nicely to 1 over 4. So that is the value of this integral. So if you find out helpful, make sure to give me a thumbs up, subscribe to my channel, support my channel, so that I will continue uploading engaging content on integral calculus. I thank you so much for watching the video, and I will see you in the next one. Bye bye.